Hello everyone, Mr. John here with this week's Thursday Tidbit, where we're going to continue talking about projectile motion and parabolas. So let's jump right in. So what were our projectile motion equations? We saw we could use a parametric equation last time. So we have our initial positions, x0 and y0. We have our initial velocities, vx0 and vy0. And then in the y direction, we have this acceleration due to gravity. So that's where this negative 4.9 t squared type of thing comes in that case. We're going to talk a little bit about some calculus in a few minutes later in this video. But in general, we don't need to worry too much about where these equations come from for right now. And our first question was, explain why this results in a parabola and what properties of parabolas might be helpful when interpreting this graph. And so that's where this simplification we'll see later of this being a parabola when it's not quite a parabola. Those things will be pretty helpful because of the properties we can take advantage of for parabolas. Now, our first goal is explaining why this results in a parabola. Now, we can take a pretty standard approach for a parametric equation in this case. So we have our equation x of t equals x0 plus vx0 t in that case. And I'm going to drop the x of t. So just remember, in this scenario, x really is a function of time, but if we're going to write it as one equation without time, we're really just looking at the x versus the y position. And so we could solve this for t, right? It's not too hard to see that if we subtract the x0 and we divide by the initial velocity in the x direction there, we can isolate the t in that scenario. Now, the key thing that I want to say here is that this is linear, right? This is linear in x there. Now, the reason I want to mention that is that I don't want to actually do all of the details with this other portion. But the main thing is that once we have this equation, we can plug in that value of t that we were solving for in the other scenario. So if we look at this, right, then I can say y is equal to, well, y0 plus vy0 t, but wait a second, what is t? T is x minus x0 divided by vx0. Now this looks a little bit messy, right? But this is where that linear comes into play again. So far, we replaced t by a linear function of x. So this is still a little bit messy, but that's still going to be just having an x in it. The degree of this thus far is just x. Likewise, when we put in the negative 4.9 t squared, so x minus x0 over vx0 quantity squared, right? If we expand all of that out, that's still going to give us a quadratic itself. So this whole thing is a quadratic. So this whole thing, if we simplify it, right, we are going to get a quadratic there, which of course means that we have the whole graph is a parabola. So the graph here is going to be a parabola in this case. So that's our situation when we're plugging everything in and solving for y in terms of x. Now, let's take a quick look here and look at what this type of thing looks like. Now, this isn't solved for x in that case, but we can look at a graph here on Desmos and look at our initial conditions and look at what our graph looks like here. So you can actually plug in that actual parametric function, but we just have a little validation then looking at that graph, and we have our parabola here on the screen. Now, couple of things I want to ignore. So I want to ignore the stuff below our y-axis, right? So let's not worry about that here. And I'll share this link later, right? If you want to play around with this a little bit, right? Changing our x and y initial velocities changes our graph and things like that there. But we have the different looks there as well. You can also change the initial conditions, but just to talk about some of these symmetries and stuff, let's leave it starting at x0 is 0 and y0 is 0. Now, the things I want to point out quickly is that because this is a parabola, then some of the things we know about parabolas are helpful, right? So this top point is at the vertex of the parabola, right? We also have symmetry about this vertex there, right? So when we kind of have this line of symmetry in that case, right, this distance, this change in x over here is equal to the change in x on the other side of that vertex, right? So these are really some of those properties of parabolas that are very helpful when we're exploring this graph in this scenario. Now this is purely in terms of y versus x now. So let me just make sure it's clear that we're graphing this function in terms of y and x in this case. So, right, when it's at the highest point, it's halfway through its total horizontal distance. It's actually half of the time as well. So there's a lot of nice connections you can draw, both with the parametric versions and the looking at the xy graph in this scenario. But we definitely do have a parabola in this case. Okay, so that is in a rough sense answering our first question here. So let's take a look then at question 2. So question 2 was, let's think actual real life examples. So you have thrown or hit baseballs, golf shots, etc. Now some of these have a little bit more complications to them, but right, in general these do not follow perfect parabolas there. So what reasons are there for this? Now, there's a lot of them that you could think of, right? So you could think of things like spins, right? So both maybe golf shots and baseballs, right? If you think of a curveball or stuff like that, right? You could think of spins, right? We're gonna not really talk about that today. The main one we want to talk about is air resistance. So air resistance, or friction if you like. So air resistance slash the friction due to the air is something that actually would happen in real life and actually would modify things a little bit. Now, you can ignore this next page. We're going to look at the graphs. They're a little bit messy, but I want to give a rough idea of what's happening here. So in general, right, we could have C some constant for air resistance. So our general situation, remember we have F, the force, right, is equal mass times acceleration. And then our normal situation is that we would have mg. So this would be our normal y direction type of thing. Now, if you've heard of vectors and stuff, I'm going to modify this into vector equations to keep in mind, okay, this force of gravity, we could think about that as a vector, right, going straight downwards. So the gravity vector, if we have our object, would be kind of pointing downward in that case. Then, right, acceleration is that vector and force is a vector too. Now this would be our parabola situation. Even as vectors, right, in the x direction, there's no gravity, so there's no force, no acceleration. In the y direction, the acceleration is gravity. The masses cancel out in this scenario. But what happens here if we look at adding the air resistance? So C is a constant here. This is like friction. So if you've done some physics, you might have talked about friction a little bit. The idea here then is that friction opposes motion. So there would be some constant for this air resistance, and it would oppose the velocity of our equation. Now, right, this is then how acceleration relates to velocity. These relate to position as well. If, right, we have a position vector or something here, this would give you some differential equations, some calculus equations that you could solve here. Now, I want to say, right, this is a little, right, messy to solve. So let me leave it at that right there. But the point is, you're going to get things that are not quite parabolas. And when we look at the picture in a second, this should make a little sense because stuff is going to be slowing down as it's going through the air, right? Air resistance is slowing it down in that case. Now, let's take a look back at our graph again. And we'll just look at this quick to compare a little bit here. So we had our original graph. Let me kind of just bump up the speeds a little bit so we have a nice bigger example to look at. And this one is our no air resistance graph, right? So this is no air resistance here. Now, what would we expect to happen if we have air resistance? Now, what's a little bit interesting here is that the mass actually does come into play in this case. So we would have a mass of the object and the constant of this air resistant there. So I'm calling this the air resistant coefficient in this case. And you see just even the x component here is a little bit messy. So I'm going to ignore that messy equation here and let's focus on the graph in this case. So here is our graph with air resistance. So if we have the air resistance, this kind of works out in that case. Now, it's a little bit shorter and it's also not quite a parabola. So it's not so clear right now, but the more air resistance we add, so let me add some more air resistance here, right? It's a little bit clearer here that it's a steeper drop off in this case. That if we add more air resistance, everything slows down and it's no longer this nice parabola that we have. So that's our main idea and things like that there. Couple things I want to say just for fun, and I will share this graph if you want to play around with these yourself a little bit. The heavier object you have, the more it kind of can resist the air resistance, right? Because it's heavier, it has more inertia. So actually, if we bump up the mass, we get closer and closer to that parabola again. And just as sometimes I like calling this a sanity check, as we reduce the air resistance, as we have less and less coefficient of air resistance, we get closer and closer to that parabola as well. Actually, C equals 0 breaks this Desmos thing, but if we want to make C very, very close to 0, right, these graphs are pretty much indistinguishable then at that case. So if the graphs are pretty much the same, we have the same parabola, but then as we bump up that air resistance again, we would get a steeper decline and it's no longer a parabola in this case. So You can play around with that a little bit more if you would like. But for now, that is a good place to stop this video. Stay tuned for a new topic next week. If you have any ideas, comment below, like the video, subscribe. It really helps us out. Otherwise, I will see everyone next time. Goodbye.